Swayam Prabha. Digital India. Educated India.
So, let us start lecture 34. We will continue our discussion on kinetics, corrosion, and now actually we are looking into the electrochemistry part, and then we will try to relate this electrochemistry to corrosion. Now, we have derived this Butler-Volmer equation, which is NF CO KO exponential minus alpha NF by RT E minus E0 minus NF CR K0 exponential minus 1 plus 1 minus alpha NF E minus E0 by RT. This is Butler-Volmer equation. And if we see the previous analysis, we see this is my I applied, and then I am replacing this Kc and Ka with these two formulas, and later we have understood that why Kc 0 equal to Ka 0, and that one we are considering K 0, we are replacing that, and we hence we are getting this Butler-Volmer equation. It has relation between Faraday current, electrode potential, and concentration of reactant as well as product, which are basically oxidant and reductant. Now, then we started saying that this particular equation can yield us Nernst equation. Now, we can do little bit of redistribution of this entire formula. I applied equal to NF K0 exponential minus alpha NF E minus E0 divided by RT minus this is CO CR exponential NF E minus E0 divided by RT into exponential minus alpha NF E minus E0 divided by RT. Then we can write equal to NF K0 exponential minus alpha NF E minus E0 divided by RT C0 minus CR exponential NF E minus E0 by RT equal to, it turns out to be then C0 minus CR exponential NF E minus E0 by RT equal to I applied divided by NF K0 exponential minus alpha NF E minus E0 by RT. So, this we are getting. Now, we see that when E equal to E0, IC equal to IA equal to I0 and I applied equal to IA minus IC equal to 0. So, that means when it is non-corroding situation or reversible situation, then this right hand side becomes 0. So, the C0 minus CR exponential would be equal to exponential NF E minus E0 by RT equal to NF E minus E0 equal to ln C0 CR or E equal to E0 plus RT NF ln C0 by CR. So, this is nothing but Nernst equation. So, we are also getting Nernst equation. So, this particular condition or the equation what we are seeing in this, they have two components, one is C0 and CR. Now, if we assume that C0 and CR are the same values, that means the physically it means that the concentration at the interface for oxidant and reductant, they are not changing and they are having the same value. So, that time it would turn out to be in this case, and then C0 if we consider CR equal to C, then I could see that I0 could have a proportionality with the C, the concentration. Now, since the concentration and this particular equation in a simplified mode can be found out if we look at this situation, this diagram. So, this diagram would enable us to get the I applied as a function of over voltage, and that time this concentration part is already inherited already included in this particular formula, which is I0 equal to NF N F nu exponential minus delta G star by RT. So, this concentration of R as well as CO, they are included here, and that time we are saying that they are equal and it becomes C. And let us see whether we can get similar sort of equations by analyzing this particular plot. This particular plot, let me redraw again. This is the over voltage related change in free energy. So, this is become NF neta, and the contribution towards the anodic side is alpha NF neta, and this part if I consider, or let us say it is alpha prime, or simply we put it alpha 1 minus alpha NF neta. This is IHP, this is OHP, this is M or R reductant, this is Mn plus or oxidant. Now, in the beginning, the free energy difference, the activation energy barrier was delta G star, and then after redistribution, when we are assuming that IA greater than IC, so this is my IA and this opposite direction flow is IC with a negative sign. This becomes my delta GA. Change in activation energy for the cathodic side would be this much. This is delta GC, and this so delta GC equal to delta G star plus 1 minus alpha NF neta. So, this plus this much, whereas delta G A equal to this delta G star minus this much. So, delta G star minus alpha NF neta, and we are assuming that alpha is equal to 0.5. That means the distribution of this total change in free energy towards the activation energy is same quantity. So, these two are equal since if alpha equal to 0.5. Now, I know that the rate of forward reaction. So, the rate of forward reaction, or it is better to say that IA. So, that means M minus equal to M n plus Ne. So, this is the forward direction IA and this is my IC. We can relate in this form NF n frequency factor and nu, this fraction of atoms that are going towards the OHP and the fraction of, this is the fraction of atom of that goes to the other end, and then exponential minus delta G A by R T. Similarly, IC can be related as NF NF nu exponential minus delta G C by R T, and this particular general equation for I is equal to nothing but NF n, which is the surface density of moles, into F, which is the fraction of atoms or ions that are going from one plane to the other plane, and this is the frequency, vibrational frequency, exponential minus activation energy divided by RT, since this is considered in terms of moles per unit area. So, now IA equal to NF NF nu exponential minus delta GA, I am just replacing these values, minus alpha NF neta divided by RT. So, this becomes NF NF nu exponential minus delta G A by RT into exponential alpha NF neta divided by RT. This part is nothing but I0, since I0 equal to NF NF nu exponential minus, sorry, here we have to put delta G star. Since delta G is delta G star minus alpha Fn NF neta delta G star by RT. So, this is I0. So, it becomes IA equal to I0 exponential alpha NF neta by RT, and similar way I can see IC equal to NF nu exponential minus delta GC by RT. So, I replace this GC with delta G star plus 1 minus alpha NF neta by RT, again NF nu exponential minus delta G star by RT into exponential minus 1 minus alpha NF neta by RT. So, this is again I0. So, IC equal to I0 exponential minus 1 minus alpha NF neta by RT. So, I applied equal to IA minus IC equal to I0 exponential alpha NF neta by RT minus exponential 1 minus alpha NF neta by RT. So, here we are considering this quantity, when we are consider this quantity to be this part and the rest part would be 1 minus alpha. So, you can also reverse, instead of taking alpha this, you can take 1 minus alpha, that time it will be reducive alpha or the reducive symmetry factor, and in this case we are considering oxidative symmetry factor. Now, once we have this, now if I compare with this particular Butler-Volmar equation here we are seeing that there are two concentration parts. Now, when we have these concentrations to be same, then we can get the same equations what we are having here. Okay. So, where in this I0 that concentration is included. So, we are not going into that part, the only we are seeing that this is also a Butler-Volmar equation. Now, this equation has got huge importance on the corrosion of a particular metal. We will look into that part, but before that, see, this neta is nothing but E minus E0, and if neta is very large, whether it is positive or negative, when it is positive it is anodic, when it is negative it is called cathodic. Interestingly, if you see that here there is a negative sign and there is a negative sign here. So, that means it is actually potential actually goes down from the reversible non corroding potential, and in the case of anodic case, if I see the anodic case where we have a positive sign in front of it. So, that means it indicates that the potential should go up from the reversible potential. But if I try to look at this equation, let us say if it is positive, let us say neta is positive and large positive, let us say neta is large positive value. So, that time if we consider this particular part, this part we